네, 시작했습니다.
Let us consider the case if the Hamiltonian is composed of H0, which is independent of time. This may include a potential, plus something that is a very small quantity, but that is dependent on time, as well as depending on the space. Then Schrödinger equation is written in the form that is the same as the original form. But I'd like to make use of the relations that I have already obtained for the H0. And is there any equations? H0 has the solutions of H0n equals ENn. And we already have noticed that if H0 is independent of time, regardless of the time evolution, the state n never make a transition to another state. It is impossible. It is not allowed to make a transition to different states. But in fact, for example, if I make a collision, this is a free particle state and final state is another free particle state. But these two states are different because of the interaction for a very short time, short period and short small area. Then make a transition from a state to another state. If it is elastic collision, the initial energy and final energy must be the same. However, the momentum direction is different. So that means that that is a kind of transition. And if I ignore that period of interaction, they are free. But here, it doesn't have to be free. It is just H0, which is composed of a free particle Hamiltonian, that is a kinetic energy, and the potential that is independent of time. And let us suppose that some interaction appears in the middle of time. Capital T is a finite time piece, and the interaction is given at a very short time in comparison with the minus infinity to the plus infinity. And I would like to develop a theory to describe that kind of time-dependent perturbation based on the previous knowledge on the time-independent perturbation theory. When we consider the time-independent perturbation theory, we also consider the potential, but at that time, the potential was independent of time. And we used the fact that we used the solution of H0, and we expressed the final state expanded in terms of the previous case, which is for H0. And the expansion was made in powers of V, and only if the case of V is a small value. If it is large enough, then we have to solve the complete equation, absolutely. However, if V is small, then we can make an approximation in series in V. Okay? Let us apply the similar way to the time-dependent perturbation theory. Okay, this solution is given inside a box. Okay, H0 has eigenstate n whose eigenenergy, energy eigenvalue is En. However, the full Hamiltonian, which is independent, which is different from H0, that is not the same as this. So I do not want to compute n, but I do want to compute just the state transition. The reason is that independently of the time-independent perturbation theory, the time-dependent perturbation theory considers the initial state and final state only. And when I measure the prepare initial state, and when I measure the final state, the two states are all expressed in terms of H0, because at the time, initially and finally, interaction never happens again. Okay? So it is enough to express everything in terms of n state. But I want to consider is during this short time period, there is evolution due to this potential V. I'd like to compute that effect. Okay? So just like the time-independent perturbation theory, we would like to express express in the basis, express the state, complete state in the basis of H0, that is n, because V is small and we can make a series expansion, and actually we consider the case of V equals 0 as t goes to plus minus infinity. Okay? This is our trial solution of this state. That means this is our new way of expressing the state as an expansion of state. If it were a state by state of H0 only, the coefficient CNT is actually n psi 0, right? So that means that CNT is independent of time, but dependence of time appears because of the time dependence of the potential. So this is the difference between this case and the previous case. Okay, if V equals 0, then psi of t has psi of t has an expansion like that, and this Cn must be independent of time. But now we consider the case depending on time. But the reason why we have factored this out, it can be understood after we completed the calculation. This factor has the energy En. That is the eigenvalue, energy eigenvalue of the nth state. That is independent of V. Okay? So if there is no V, that factor always appears. So I'd like to ignore that factor in our calculation, because that is just, even though that is time-dependent function, that appears always. So we would like to ignore or even consider as a state cat that has been translated by using the unitary operation. E to the I theta n, whose complex conjugate is n e to the minus I theta. Whether theta is depending on time or not, if I square it, it is the same as this, right? So I can always redefine a state by multiplying phase factor that cancels when I square. So the probability is always conserved, and that does not change any physics. The evolution effect of V is not taken into account yet. Evolution effect of H0 has been included only. So I have to consider that factor, and that is included in C and T, right? If I assume this is 0, it is wrong. Okay, so let us make use of this state, and we already know that this n is not for the eigenstate of H, but for the eigenstate of H0. So I can replace En by H0, right? So we remember the Hamiltonian is the time evolving operator, and IH bar partial time derivative is the Hamiltonian. And if I multiply minus H bar minus I over H bar to both sides, that is, time derivative can be expressed as minus I 8 over H bar Hamiltonian. And the full Hamiltonian is a sum of the original Hamiltonian, unperturbed Hamiltonian H0 plus interaction potential, right? So let us compute the time derivative of the state cat using time derivative, and right hand side using H0 and potential. So if I make an operation of this operator to the state side using the expansion, trial expansion given here, I have this vector. And let us divide these two pieces separately. If I multiply this one to here, H0 does not act on this complex number. H0 always acts on the other operator or state. And H0 commutes with H0, exponential H0. And this is the first term, okay? And potential is here. This is the second term. You know, exponential minus I over H by H0t, whose, if I take the time derivative, what I get is the same operator, and over vector is just the coefficient of time t. Therefore, minus I h bar h0 can be understood as a time derivative of this whole thing, except for this coefficient c and t. So I have sum of n, c and t, and partial time derivative of this state. Okay? And then next is, I just copy this one, and v is here. Remember, v can be an operator, so I did not commute with other thing. But Cn is still a complex number that can commute with other things. And I just copied this vector. All right. If I directly evaluate the time derivative of this state, what happens? The state is here. If I take the time derivative, I have time derivative of Cn and time derivative of this time evolution operator. And if I take the time derivative of time evolution operator, what I get is, where is it? This guy. And this guy, I don't have to expand this because I have simplified it already. So left hand side, right hand side, if I compare this, they cancel exactly. So remaining piece is the potential dependent part and the time derivative of coefficient Cn. Okay, let's see. If I consider this whole thing as a new state, redefined state as n prime, what happens? I already told you that even though I have a phase change, if this change of variable, a change of state does not change the probability. So I define this guy to be n prime, then what's happening is this guy is the same as this. So I factor these out, and left hand side is sum over n of time derivative of nth state summed over n prime equals minus I over h bar vcn and n. But here, because this is a dummy variable, I used m instead of n. The reason is that v is an operator. So after acting on this state does not have to be proportional to m. It may have different components other than m. If I have written this index to be n and made it proportional to each other, then I would have made a mistake. So I have n prime, and re-express this one, inserting the identity operator that is sum over n. This projection operator can be inserted here. Okay? Then this is a primed one. Then I would have move this right hand side to the left hand side and combine everything by factoring out nth state. Then this is the same as the time derivative of nth state, and this is plus I over h bar. And if I substitute this guy, then this is n prime is here, and v operator m prime and multiplied by Cn.
시그마가 있어요. 시그마, sum m, sum over.
Right. This is sum over m. If I make use of matrix notation, this is vector, column vector C, time derivative of column vector C is minus I over H bar, V matrix, and C column vector. So, for example, if we has this kind of matrix form, then initial state is 1, 0, then 1, 0 can make a transition to 0, 1, depending on this time evolution equation. Okay?